Hello everyone and welcome back. In some of our more recent videos, we've been discussing energy, particularly work, which is the transfer of energy, gravitational potential energy, and kinetic energy. We have two more types of energy to discuss, and one of them is elastic potential energy, the energy stored in an elastic object. But before we can talk about that, we need to discuss a particular property that all elastic objects have. And there is no elastic object that you're given more often in a first-year physics course than the spring. So we are going to center this discussion around springs. To begin, let's bring up a hypothetical question. I give you two springs, a red spring and a green spring. They are both the same size and same length, and I ask you, which of these two springs is the stronger spring? Now that's how we talk about it in our casual language. Which spring is stronger? Now naturally, one thing you would do immediately is start pulling on them. So let's say we locked both of them down on one side. So the left side of these springs cannot move, and you pull them both in this direction. So you pull them both so they stretch to this line, which means the springs literally got longer. The green spring pulls on you with this much force. The red spring pulls on you with this much force. So pulling them both the same length, you feel the force pulling on your hand from both springs, and you conclude that the green spring is the stronger spring. Now, one thing to note about this, the more you pull the spring, the more force it will exert on you. So let's say you pulled the red spring all the way to here, and the red spring now exerts this much force on you. So from the rest position, if you were to compare this displacement for the green spring and this displacement for the red spring, that would be an unfair comparison because a property of the spring is the larger the displacement, the larger the force a spring will exert on you. So the only fair comparison is if you actually made the displacement the same for both of them. And if you do that, the green spring pulls with more force, therefore you would say that is a stronger spring. Now again, that's how we talk about it in our casual language. However, there is an actual physics variable that represents how strong a spring is, and that's what we're going to discuss. Now to actually analyze this property, let's actually get some values in place. So here I have a spring. The spring is a certain length. I have a rest position here for the end of the spring. I have a claw, which can grab the end of the spring. And I have a number here representing the displacement of the spring, how far I've pulled it or pushed it. So to visually show you a property I was just discussing, pulling the spring a little bit, this blue vector represents the force spring on object. In other words, the force the spring is exerting on the claw. The more I pull the spring, the larger that force gets. So what immediately separates this from the other forces we've been dealing with is this is a variable force. This force changes as displacement changes. And not only that, notice if I pull the spring to the right, the spring is always trying to get back to its initial position. In other words, the spring is constantly trying to get back to its original length, also called its relaxed length. So here's the spring back at 0. If I were to push the spring in, the displacement is now to the left and the spring is pushing to the right. So again, the spring is always exerting a force on the object in order to try to get back into its original position. So I'm going to let go of the spring, and now let's actually do a little experiment here. I'm going to apply forces to the spring. But right now, we're going to start with this data point. Nothing is touching the spring, so the spring is not exerting any force on any objects, and the displacement is 0. I will now exert 6 newtons on the spring. We have a displacement of 0.05 meters, and the spring is exerting 6 newtons on my claw. I will increase that to 12 newtons, and the spring is now displaced 0.1 meters. 18 newtons, I'm at 0.15 meters. 24 newtons, I'm at 0.2 meters. 30 newtons, I'm at 0.25 meters. 36 newtons, I'm at 0.3 meters. 42 newtons, I'm at 0.35 meters. 48 newtons, I'm at 0.4 meters. And this will be my last data point. If the spring exerts 54 newtons on the claw, the spring has been stretched 0.45 meters. So in order to analyze this, we're going to take those data points and graph them. Now, if I take the data we just observed and put it in a graph of force spring on object versus displacement, I will get something like this. In fact, I will get exactly this. I have force spring on object on the y-axis and the displacement on the x-axis. And as you notice, this is a linear relationship. In other words, the slope is constant. And one of the things I mentioned earlier when we did graphing is one of the things you need to understand on a graph in physics is what the slope represents. So let's check it out. First and foremost, I'm going to apply the oldest thing you've ever learned about slope, which is rise over run. I'm going to do that with the units. If I do rise over run with the units, I get newtons per meter. So this is the unit of the slope. Now, if you notice, that means for every equal distance that I pull that spring, it is exerting a proportional amount of force based on that displacement. In other words, force spring on object over the displacement gives me a constant value. So for this spring, for every equal amount of displacement you pull the spring, you will get an equal increase in force. So this value literally represents how strong the spring is, and it actually has its own name. It is called the spring constant, a variable representing how strong a spring or elastic object is. The symbol for a spring constant is a lowercase k, and we have already discussed the unit, which is newtons per meter. Now, putting down what we just found out again, that would mean for spring on object over displacement equals k. If I rearrange this, I'll get force spring on object equals k delta d. So using this, you could predict how much force the spring will exert if you know its spring constant and how far you push it or pull it. Now, there's actually one small problem with this equation, and that is the fact that displacement and force are both vectors. And going back to the simulation here, if the displacement is positive, which means to the right, the green arrow, force spring on object is negative, to the left. If the displacement is negative, then force spring on object is positive. Now, it's important to note that k can never be negative. K is a representation of how much force the spring will exert on an object, depending on how far you push it or pull it, regardless of direction. It is a natural property of the spring. So in other words, K is always absolute value. It is never negative. Displacement can be positive or negative, and force can be positive or negative. And as we just saw, they're always opposite each other. So a very simple addition we're going to make to this equation is that. So K is not negative. That negative is actually in the equation. So this relationship describes the force a spring will exert on an object depending on its spring constant and how far it is stretched or scrunched from its rest position. So going back to my original springs, it could be said the green spring has a spring constant of 20 newtons per meter, and the red spring has a spring constant of 8 newtons per meter. If you knew these values before you touched the spring, you would know if you stretch them both the same length that the green spring would exert more force on you. So spring constant is literally a representation of how strong the spring is. This relationship is what is known as Hooke's law. Let's take it and actually do a quick problem that involves it. So this is a pretty common setup. A spring with a relaxed length of 1.5 meters is hung from one end. It has a spring constant of 98 newtons per meter. If a 3.0 kilogram mass is hung from the spring, how long will it become? In other words, what will the new length of the spring be? So here is my spring. Current length is 1.5 meters. Now I'm going to hang a 3 kilogram mass on the spring, which will cause it to stretch, which means this represents displacement. Now to solve this, we're going to use Hooke's law, but right now we have the spring constant, which I'll list. K is 80 newtons per meter, but we are missing the force. And to get it, we're going to do a force diagram of this hanging mass. I'll do the force diagram on the side so nothing gets in the way. For starters, I'm going to start with the force we usually start with. Force Earth on object is mg, 3 kilograms times 9.8 newtons per kilogram, and I get 29.4 newtons. Well, this mass is at rest. It is not going anywhere, which means I need a force opposing that, and this, of course, is force spring on object. And if this mass is not going anywhere, it has no acceleration, therefore net force is 0, therefore force spring on object must be 29.4 newtons. So I now have force spring. I will take Hooke's law, I will rearrange it for displacement, negative force spring on object over K, negative, my force is upward, so it's staying positive, 29.4 newtons. K is always absolute value, it is never negative, 80 newtons per meter. I'm dividing by a fraction, so newtons cancel, meters end up on top, and I would get negative 0.368 meters. Now, what is this? This is the displacement. Is this my answer? No, it is not, because the problem did not ask for displacement. It asked for the new length from the spring. Why is it negative? It is negative because it's stretched downward, which is perfectly fine. So, if this is length initial, that means length final would be length initial plus the change in length, which would be 1.5 meters, and this spring got larger by 0.368 meters, which means length final is 1.868 meters. And there you have it. Even though displacement is negative, I know that negative means I'm stretching the spring to make it longer. You could say you're simply measuring the length from top measuring downward, but another way to put it is length is a scalar. Length is not a vector. So since you know that displacement is adding to the length, just make it absolute value and add the two together. But just to note, this situation is extremely common, and this is a force diagram you're going to want to remember, because you're going to need to use it in order to find force spring on object. So to finish up, let's go back to my graph here. I had this blue line, which represented the spring I showed you. Now, let's say I have this green line and this red line representing two more springs. So let's say I have spring A, spring B, and spring C. And I ask, which of these is the strongest spring? Well, looking at the slope, the green spring would have the largest spring constant. It is pretty much about 60 newtons per 0.1 meters, which would be approximately 600 newtons per meter. C is about 20 over 0.4 meters, which is about 50 newtons per meter. And B, the one I showed you, was 120 newtons per meter. So the slope of this line literally will find you the spring constant. So Hooke's law is usually written like this. Force spring equals negative K delta D. Technically, it's force spring on object, but you have the idea. While we're here, there's one more thing we need to discuss. The other thing I mentioned you should always look into about a graph is what the area under the curve means. So for this red spring, that means the area under here. This is obviously a triangle shape, and the area of a triangle is 1/2 height times base. If I just look at the units here, I get newtons times meters, and that should look familiar because we did it recently. Work is force parallel times displacement. And if you apply a force to the spring, is that force and displacement parallel? Yes, they are. Notice this time my force arrow is red, means this is the force applied from the claw, not the spring. I pull it to the right, displacement to the right, which means, by my definition and equation of work, I am adding energy to the spring. In other words, I'm transferring energy to the spring, which means work is being done, and that is true either way. Force is positive, displacement is positive, positive work. Force is negative, displacement is negative, positive work. I'm transferring energy to the spring the more I scrunch this in. Now, that means in this graph, if I do 1/2 height, which is force spring on object, times base, which is displacement, I will get work, the amount of energy transferred. Why is the half here? Well, this force is not constant. Everything we've done involving the work equation so far has involved a constant parallel force. Let's say force spring is 20 newtons at this point, and it is 0.4 meters in displacement. If you take the spring and you pull it back, you're not using 20 newtons the entire time. In fact, if you don't touch the spring, the force you exert is 0. You pull this a quarter of the way and you're exerting 5 newtons. You pull it half away, you're exerting 10. You pull it 3/4 of the way, you're exerting 15. You pull it all the way, you're exerting 20 newtons. So force is increasing as you pull it back. And remember, this is an average force. So if you're holding it at 0.4 meters and exerting 20 newtons, you did not exert 20 newtons the entire time. You started at 0 and worked your way up to 20 newtons, which means your average force, which would be 1/2 times 20 newtons, would be 10 newtons, times 0.4 meters would be 4 joules. In other words, that would be how much work was done on the system. And notice this is positive if you are stretching the spring or scrunching the spring. So that means we have something else to say today that is important, and that is the area under a force versus displacement graph represents the work done on the system. So today we discussed spring constant, its symbol, its units, Hooke's law, which is the relationship between force spring on object, spring constant, and how far you push or pull the spring, We talked about the force versus displacement graphs involving a spring. The slope represents a spring constant, and the area under that line represents the work done on the system, which in this case is going to be the spring. And this is something that's going to come into play when we talk about elastic potential energy, but I will save that for next time. So for now, I'll say have a good day. This is Mr. M signing off.